So let us see what is matrices. Matrices, it is defined as a rectangular arrangement of elements or numbers. Rectangular arrangement of elements of numbers is a matrix. It is singular matrix and matrices is a plural. Example, A is equal to, you see we are denoting in a square bracket inside. No comma is in between, only numbers must be separated with the spaces. So the horizontal arrangement, this horizontal arrangement is called a row. There are two rows, first row is R1, second row is R2, and there are three columns C1, C2, C3. And it is reading like this: A is equal to matrix 2, 3, minus 1, 5, 4, 3. First we will read row wise we are reading it. Rows. A is equal to 2, 3, minus 1, 5, 4, 3. So we are saying there are two rows and three columns. So we'll say A is a 2 into 3, but reading as 2 by 3 matrix. 2 by 3 matrix. A is a 2 by 3. Number of rows we will write first, that is there are 2 rows, and number of columns we will write after that, that is 3. And you may see that 2 into 3, 6 elements are present here also. It's a 2 by 3 matrix. And its elements are denoted by Aij, where I is the position of row and J is the position of column. Means if you are taking I as 1 and J as 1, A11 means the element present the first row, first column, that is 2. A11, first row, first column, that is 2. A12 means first row, second column. First row, second column, that is 3. A13 means first row, third column, that is minus 1. A21 means second row, first column. Second row, first column, that is 5. A22 means second row, second column, that is 4. Similarly, A23 is second row, third column, that is 3. So this is the position. Every element having a position. We are denoting by generally Aij. I can be the number of rows, whatever the rows are there, and J is number of columns. Now a simple question is that construct a 3 by 2 matrix, means there must be 3 rows and 2 columns whose elements are Aij is equal to I plus 2j by 3. I is the row and J is the column. So I made that matrix A is equal to, since there are 3 rows, I made 1, 2, 3 rows and 2 columns. So there are 1, 2 columns, that is by 3 by 2. Okay. So 1 means I is 1, J is 1. So when I is 1, J is 1, 1 plus 2 upon 3, 3 upon 3, that is 1. I1, J2. A12 means I1, J2. 1 plus 4 upon 3, that is 5 by 3. Similarly, 2, means I2, J1. 2 plus 2 upon 3, that is 4 by 3. A2 is, just put that I as the first element, J as the second element, the rest you will get it like this: 4 by 3, 2, 5 by 3, 7. Putting this. Another question is that if a matrix contains 15 elements, then possible order. What are the possible order? There may be 1 row and 15 column. So 1 into 15 matrix, 1 by 15 matrix. There may be 15 rows and 1 column. 15 rows and 1 column. There may be 3 rows and 5 columns. So 3 into 5, 15 and 5 into 3, like that. So what are the factors possible we have written there? If it is 20, then 1 by 20, 20 by 1, then 2 by 10, 10 by 2. Then 5 into 4, 4 into 5, like that, different possibilities of that 20 factors we'll write and we'll say how many possible orders it may have. So it may ask in the examination how many possible orders are there. So 1, 2, 3, 4 in this question there are 4 possible orders. Now, there are some types of matrix. What is column matrix? If in a matrix there is only one column, this is what is column, and any number of rows. So that is called a column matrix. So is here only one column, any number of rows, anything. So 3 by 1. So always in a column matrix, the order end point will be always 1. 3 by 1, yeah, m by 1. So a column matrix always of the form a number by 1. Second part always 1. Similarly, row matrix, there must be only one row and any columns. You see any number of columns. So it's a 1 by 4. One row, 1, 2, 3, 4 columns. So in a column matrix, sorry, in a row matrix, always 1 into a number is there. 1 by a number means 1 into the form 1 by m or 1 by n form. Whatever it may be, a number will come here. Only one row, any number of rows. Here, one column, any number of rows. Then square matrix. Number of rows is equal to number of columns. How many rows are there? That much columns are also present. You see, A is equal to 5. One row, one column, 1 by 1 matrix. B is equal to 3, 5 minus 1 to 2 rows and 2 columns, 2 by 2 matrix. But a square matrix you may write in short like this also. B is a square matrix of order 2. Since both the rows and columns are same, if we are using the word square, B is a square matrix. So square matrix means rows and columns are same. So no need to say both the orders, it is enough to say of order 2. Both are same. B is a square matrix of order 2. Now what is the importance of square matrix? Square matrix only having diagonal elements. You may see there are two diagonals, 1, 3, 2 is one of that and other is minus 1, 5. But we will consider only this 3, 2 as the diagonal element. This main elements only. This is the diagonal we will use, the other one we will not use as diagonal. So this is the main diagonal. So that diagonal elements are present only in a square matrix. The next definition is diagonal matrix. What is a diagonal matrix? Diagonal matrix must be a square matrix in which all the non-diagonal elements. Non-diagonal elements means other than diagonal elements. These are the diagonal elements. All the non-diagonal elements must be 0. So it must be a square matrix. So diagonal matrix must be a square matrix. It is compulsory in which all the non-diagonal elements. Diagonal elements may or may not be 0. Diagonal elements can be anything. But non-diagonal elements must be 0. All the non-diagonal elements must be 0. Then the next one is scalar matrix. Scalar matrix is a diagonal matrix. It is also a diagonal matrix, means it must be square matrix as well as all the non-diagonal elements are zeros. And scalar matrix means this diagonal elements are always equal. Means diagonal you are starting with the 5, then all the diagonal elements must be 5. 3 if you are writing, then all the diagonal must be same. This diagonal elements must be same. Then the most important one is coming is identity matrix. Identity matrix must be a scalar matrix, means it must be a square matrix, it must be a diagonal matrix. Okay, all that satisfying. So scalar matrix. So identity matrix must be a scalar matrix in which the diagonal elements you can use only one. One only you can use as diagonal elements, then it is identity. Here you can use anything, scalar matrix, you can write any number. So means every identity matrix must be a scalar matrix, but every scalar matrix is not an identity matrix. So identity matrix of order 1, I1, it is denoted by 1, I1. I2 means 1, 0, 0, 1, diagonal, 2 order. I3, 1, 0, 0, 0, 1, 0, 0, 0, 1, the order is 3 by 3. All these you may denote it by I also. The identity matrix you may denote it by capital letter I also, single I. So the order depends upon the situation. This I you can use for the identity matrix. Since the order is clear, so it is I1, I2, I3 is written there. So let us see some other types of matrices. Next is zero matrix or null matrix. If every element of a matrix are zero, every element is zero, then we can say it is a zero matrix. It can be of any order, and it is denoted by capital letter O. Every element is 0. None of none of the element you can write non-zero. So all the elements must be 0. Equal matrix. Suppose you want to say two matrices are equal. So if you want to equate two matrices, it is possible only when they having both of them having same order. If A is a 2 by 3 matrix, then B also must be 2 by 3. Then only you can equate it. So if you want to say two matrices are equal, first check their order. Both the orders are same. Then only you can equate, and corresponding elements also must be equal. So it is a 2 by 2 matrix, and here also 2 by 2 matrix. And the first element must be equal to first element, that is Z must be equal to 3. 5 minus 2x must be equal to 3, so x must be 1. 3y is equal to 6, so y is equal to 2. And 4x plus z, so 4 into x, 4 into 1 plus z is 0. 4 plus 3, that is equal to 7. So you can equate it like that. It's possible to get only when their order are equal and the corresponding elements are also equal. So how to operate on matrices? Suppose I want to add or subtract two matrices, addition and subtraction. So how to add or subtract? So here also addition, subtraction also possible only when both of them having same order. And only you have to add or subtract the corresponding element. Suppose A, here it is 2 by 3, B also 2 by 3. So I can find out A plus B and A minus B. A plus B corresponding elements, you add 3 plus 1, 2 plus 2, minus 1 plus 4. Similarly, corresponding elements add, you will get same order matrix as sum also, difference also. And difference you have to subtract. 3 minus 1, A minus B, 3 minus 1, 2 minus 2, 0, minus 1, minus 1, like that you will get A minus B. Now if you want to multiply matrix by a constant, non-zero constant, so that constant must be multiplied everywhere. So suppose I want to multiply A with 2, so 2 must be multiplied with every element. 2 into 3 is 6, 4, 2 into minus 1, so everywhere we have to multiply. Similarly minus 3, so minus 3 must be multiplied every element. Minus 3, minus 6 and so on. You can multiply correspondingly. So it's a very simple direct method. But multiplication is the most important thing. So here multiplication of matrices is possible only when number of elements of the first number of elements in number of columns, not the number of elements. Number of columns of the first matrix is equal to number of rows of the second. Then only you can multiply. Means here the order, if I am checking, this is 3 by 2. So if I am writing its order, this is a 3 by 2 matrix and this is also a 3 by 2 matrix. I cannot multiply here. Number of columns is 2. Number of columns is 2, but here number of rows is 3. So I cannot multiply AB. But here you see I can multiply here. A is of order 2 by 3 and B is of order 3 by 1. You see this 3 and 3 are same. So number of columns of the first matrix 1, 2, 3. Number of columns of the first matrix will be number of rows. So it can be multiplied, and after multiplication you will get the result as 2 by 1. But this equal things will go away from here. So you will get 2 by 1. Here AB is possible to multiply, but BA cannot be. If you are reverse order multiplying, not possible. Here the number of rows and columns will make you trouble. So how to multiply? Let's see. AB, how can you multiply? So in multiplication, first you check this one. Number of columns of the first equal to number of rows of the second. Then only multiplication possible. Then how to multiply? You take a row of the first matrix. Take a row of the first matrix and multiply the corresponding elements of the columns and take their sum. Means I want to get the AB result. This one of the element, this minus 2, I can get it. This row multiplied with this column, corresponding element multiply and take the sum. 3 into 1, that is 3. 2 into minus 1, that is minus 2. And minus 1 into 3, that is minus 3. So total you are getting minus 2. And similarly second row you take and do the same procedure. 5 into 1, 5. 4 into minus 1, minus 4. 3 into 3, 9. Total we are taking 10. And as I told you, the resultant must be of 2 by 1 order. Means this 3 and this 3 we are removing. The remaining things will be there 3 by 1. So it is written there. A row of the first column multiplied with a column of the second. First a row of the first, sorry, column, row of the first matrix. So the first matrix multiplied with the column of the second, one element of the resultant can be obtained by taking the sum of the product of corresponding elements of a row with the column. As I told you, taking the sum of the product of corresponding elements of a row with a column. So that's a procedure. So multiplication is little important and little difficult also. So you have to practice more to get. I will give you some other examples after this. Some other examples I will give you. Now here are some examples of matrix multiplication. I took A as a 3 by 3 matrix and B as a 3 by 2 matrix. Multiplication of AB is possible because number of columns of A is 3 and the number of rows of B is 3. So interior things are equal. So if you are multiplying, the result will come 3 by 2 matrix, that is here multiplied. So how the multiplication, I circled the first row and first column. A row of the first matrix is multiplied with the column of the second. Corresponding elements multiplied and add. You see that 2, 3, 6, 3 into 1. Here row, here column. 3 into 1, 3. 1 into minus 1, minus 1. This total will come 8. Similarly, same row multiplied with the next column. 2, 2, 4. 3 into 4, 12. 1 into 2, that is 2. Total you will get 18. Now if again column is there, multiply and continue here. So column is completed. Now take the second row and do the same procedure. Second row multiply with the first column. Minus 1 into 3, 0 into 1, 4 into minus 1. Total will come minus 7. Again minus 1 into 2, 0 into 4, 4 into 2. Total will come 6. Now third row do the same procedure. Third row into this. 1 into 3, 2 into 1, 6 into minus 1. Similarly 1 into 2, 2 into 4, 6 into 2. Total will come 22 and 3 by 2 order itself is coming. But if you are finding B order is 3 by 2 and 3 by 3. So BA is not defined because the number of column is 2, number of rows is 3. It cannot be multiplied, so not defined. BA is not defined. So you may see that AB sometimes defined at the same time BA may not be defined. Means AB is not equal to BA. Commutative property is not satisfied. Now A square. A square means same matrix multiplied 2 times. It is only possible with the square matrices. Otherwise square cannot be calculated. So A into A multiplied. You will get a square matrix of same order. Multiply the row with the column. 2, 2, 4, minus 3 plus 1, total 6. Like that, everywhere multiply. You multiply and see, you will get this result. A square means same matrix into same matrix. B square is not defined because B is not a square matrix. You cannot multiply, it is not defined because B is not a square matrix. Now some of the important things, commutative property not satisfy, AB not equal to B. A matrix multiplication is not commutative but associative. But associative, keep it in mind. A, B, C are 3 matrices. You may multiply AB as well as BC. If multiplication of AB and BC is possible, then first multiply BC with A or multiply AB with C. That is what is called associative property. It will satisfy associative property. Matrix multiplication is associative. You see A plus B the whole square means A plus B into A plus B. If you are opening the bracket, you will get A square plus B square plus AB plus BA. But it is not equal to A plus B the whole square because AB and B are not same. So you cannot write A plus B the whole square equal to A plus B the whole square is equal to this one. This you cannot write A square plus B square plus 2AB is not equal to A square plus B square plus 2AB. I cannot write. The reason is AB not equal to BA. Now transpose. What is the meaning of transpose? Is Interchange the row and column. Row you convert it into column. Interchange the rows and column of a matrix A. It is denoted by A dash or A bar or A raised to capital T or small t. Usually using the first term, A dash means interchange the row and column of the given matrix A. Here A is a matrix given 1, 2, 3 minus 1, 1, 3. So A transpose means this row will come as column, second row will come as second row. It is a 2 by 3 matrix, but it is a 3 by 2 matrix. So if you are finding its transpose of the transpose, continuously if you are taking any transpose, you will get the starting matrix back. If you are again interchanging row and column, you will get the original matrix back. So transpose of the transpose is same matrix. Now, what is a symmetric matrix? Symmetric matrix means it must be a square matrix, then only symmetric the word is possible. If the transpose of a square matrix is that itself, that is written, square matrix A is symmetric if and only if A transpose equal to A. If the square transpose of a square matrix is a same result. You see, one example is written. If you are taking the transpose, you will get the same matrix back. It is possible. It is possible only with the square matrix. Such a matrix is called a symmetric matrix, and another is called a skew symmetric matrix. If the transpose is negative of A, transpose is negative of, see this matrix. If you are taking the transpose, then its negative will come. If I am taking the transpose, you take it, transpose will come negative. So skew symmetric matrix having an important. Both of this must be square matrix as well as diagonal elements of a skew symmetric matrix are always 0. If the diagonal elements are not 0, if any one of the diagonal elements is not 0, never that matrix is a skew symmetric matrix. No such property is here. In a symmetric matrix, diagonal elements can be anything, but in a skew symmetric matrix, diagonal element must be 0. Then only it is a possibility of a skew symmetric. That doesn't mean that always skew symmetric. Then you have to check the transpose is coming negative or not. Some properties of transpose is written. Already I told you a transpose of transpose equal to A. Transpose of the transpose is same matrix. Plus or minus, you can take the transpose directly inside. Transpose you can take it directly inside. Constant you multiply with the matrix and take the transpose, or constant you put it outside and multiply with transpose, not a problem. One example is written. 2 into A, the whole transpose is same as 2 you make up. There is no transpose for a number. 2 is a constant. I put it outside. Here K is not a matrix. Number. Say the real number other than 0. 2 into A transpose. This result always remains same, and this is the important result which are useful. AB the whole transpose is B transpose into A transpose. Transpose, when it is going inside, it will interchange the order. So let us see an important result. Every square matrix can be expressed as sum of symmetric and skew symmetric matrices. Means you take any square matrix, we can write, we can split it into two matrices in which one is symmetric and other is skew symmetric. So the how actually it is there. So I took A as a square matrix. A can be written as half of A plus A transpose plus half of A minus A transpose. Means this RHS, if you are simplifying, you will get half A plus half A, that is A. A you will get back. In which A plus A transpose is symmetric, which I told you earlier, and A minus A transpose is skew symmetric. This constant will not affect because the transpose of a constant is not there. So, because already we have written a property, K into a constant into a transpose, K you take inside the transpose or outside the transpose, there is no problem. So this is symmetric and skew symmetric. One example is written A transpose. Half of A plus A transpose I calculated. You added and simplified. You may see that this is symmetric because its transpose will come same matrix. And half of A minus A transpose, this you may see that it is skew symmetric. we are taking its transpose, it will get its negative. Now here took another one, A and B are two matrices, AB equal to this, you multiply. AB the whole transpose means interchange the row and column. And B transpose into A transpose, if we are simplifying, B transpose interchange rows and columns of B and then followed by A. You may see that AB transpose, AB the whole transpose you will get, it means you will get the same result here. So AB the whole transpose is same as B transpose into A transpose. Now if A and B are symmetric matrices of same order, then AB plus BA is always symmetric and AB minus BA is skew symmetric. Its proof is written here. It is given that symmetric matrices A and B. So A transpose is A, B transpose is B. I want to prove is symmetric. So its transpose you will get the same. You see that. I took transpose inside because in plus and minus we can take directly inside. And B transpose into A transpose, here I use the property. Then B transpose is B, written here, B transpose is B and A transpose is A. Use that result and simplifying, you will get where I scattered the transpose, that itself. So we can say this is AB plus BA is symmetric. Similarly, you may see that AB minus BA the whole transpose is it's negative. So AB minus BA is symmetric. Skew symmetric. And it may be asked as one mark question also or assertion reason also. So result is important, proof is not that much important. Now here also another result, this result is also important. B transpose AB, one matrix is written here and other two matrices, one is the transpose of the other. Then this is symmetric or skew symmetric, depends upon A. If A is symmetric, then this complete matrix is symmetric. If A is skew symmetric, then this complete matrix is skew symmetric. This is also result. So in between letter depend. So if this is symmetric, means A transpose is A. We are taking A transpose is equal to A, then this complete will be symmetric. If we are taking A transpose equal to minus A, then this complete will be skew symmetric. That is written. Then if A and I are square matrices of same order, then A into I is just considering as a one of multiplication, identity matrix, identity number. So A into I into A always will remains A. Means identity matrix we are multiplying. With any matrix, if multiplication is possible, then always that matrix itself is there. Similarly, square, cube raised to 4, any power of identity matrix is I itself, identity matrix itself.